Hello again. In the first part of this video, we discuss continuous descent on final approach in general, including the use of the CDFA table in the Canadian Instrument Approach Procedure charts to pick the top of descent point when CDFA techniques are being used. Now we'll look at how it works out in the air, specifically on an approach to my home airfield of Pembroke, Ontario. I'll start by showing you how the top of descent would be selected at Pembroke and how the various altitudes are corrected to account for such things as using a remote altimeter setting and for the inherent errors in a barometric altimeter when temperatures are non-standard. These corrections are a lot of work and are error prone. Hopefully by the time I get through that, you'll be convinced that there has to be a better way. I'll show you how I handle the problem, then we'll go flying. Due to the restricted airspace to the north, the only approaches at Pembroke are to runway 35. The RNAV 35 is a little more complicated than the one at Kirkland Lake because there's a step-down fix between the FAF and the runway. Also, like most RNAV approaches, there are no circling minimums. That begs the question, what do you do if the wind is favouring runway 17? There's only one other airport in Ontario where this situation arises, so I'll discuss this later under unusual approaches. To avoid having to fly a separate demonstration, I'd like to include a two-stage descent, like the one we saw at Saint-Jean, Quebec in part 1. So we'll pretend that the sector safety altitude is 4,500 feet, as opposed to the published 3,000. Also, to provide the most comprehensive demo, we'll assume that the local altimeter setting is not available, and that temperature correction appropriate to a minus 20 degrees centigrade day will be required. As you approach your destination, one of the first things you do is check the weather. You can either monitor the ATIS, ask Centre for the latest METARs, or look at the METAR on Sirius XM if you have in-cockpit weather. You want to determine the approach in use, the ceiling and visibility, and the altimeter setting. If it's a cold day, you also want to know the reported temperature, as you may need that to correct the published altitudes for low temperature. At Pembroke, weather reporting has recently become problematic. We used to use the METAR for Petawawa, which is just a few miles north, but METARs there may or may not be available since COVID. If there's a Unicom operator around, you'll be able to get the altimeter setting and maybe even the temperature and winds. If there's no local altimeter setting, you have to use Ottawa's and add 160 feet to all published altitudes. At Pembroke, the airport is not in a radar environment, so you won't be getting vectors to final. You'll transition via one of the published initial approach fixes. In this demo, we'll be arriving from the southeast, so we'll use Bondi. First, let's look at the top of descent we'll use. The recommended top of descent, or TOD, is 2,000 feet, but that's right on top of the FAF, so we'll pick our own. Using my 2 miles to the FAF rule, we need at least the slope height at 6 miles, which is 2,510, call it 2,500. That would give 2,000 feet to be lost in the initial descent. If we cross Bondi at the 4,500 minimum safe altitude, we have about 4 miles before we start the turn to final. So even at a steep 500 feet per mile, we just make it. What if we move the top of descent a bit further back to the 7-mile number of 2,830 feet? Then we'd only have to lose 1,700 feet. At 400 feet per mile, that occupies 4.2 miles. At the steeper 500 feet per mile, we'd be level in 3.7 miles. So I'll pick my top of descent of 7 miles and 2,800 feet, with an initial best effort immediately after crossing Bondi. We certainly wouldn't want to transition direct VIXIB, as that would mean an impossibly rapid descent from 4500 after joining final. If you're unable to display your distance to the missed approach point, note the 2.8 mile distance back from Kassam for your top of descent. Now I'm going to show you the steps you'd have to go through if you're using the barometric altimeter as your altitude reference. Since my handwriting is poor, I'll use a spreadsheet and show you the results as we go along. The first thing we'll do is make a list of the altitudes involved in the approach. There are 6 of them, which I've ringed here. Fortunately for me, there's only one approach at Pembroke, the RNAV runway 35, so I can do this part in armchair comfort, but you may have to do it in a bumpy airplane in IMC. We're supposed to correct all of these if we're using a remote altimeter source and or if the temperature at the altimeter source is below 0. The first one's easy, just add 160 feet to all these numbers. But even that you will want to write down. Here are the heights of the altitudes I circled, with the remote altimeter setting correction of 160 feet applied. What's not clear is what you do if no remote altimeter source is specified. There must be lots of remote airports where this is the case. No doubt if we're talking airlines, they'll make sure they have an operator on hand on the ground to give them the altimeter. But for the rest of us, what do? Go somewhere else, I guess. Here's the table with the temperature corrections added in. I got these numbers by looking up the temperature correction table on page 35 of the CAP General for all 6 points. That was a lot of work to accomplish in a short time in the air, and it was certainly error-prone. As we'll see, there are a couple of ways to reduce the workload. By the way, you're supposed to advise ATC if you are applying temperature corrections to your barometric altitude. That would be particularly important for the missed approach hold altitude. They may have somebody holding there at an assigned barometric altitude. There are several apps that eliminate the table lookup work, but as long as your reference is the barometric altimeter, you'll still have to work out the numbers for all 6 altitudes and note down the results. Hopefully, the answers from this app that I found on the App Store will match those I showed on the last slide. I wonder if anybody else thinks that this temperature correction stuff is too much work. Apparently, the FAA thinks so. They've designated a short list of airports where temperature correction is required and the temperature below which you must apply it. They're called snowflake airports. You can view this list on the internet. The classic example is Aspen, Colorado, but there's an example of one nearer home that's in lower lying country. Elmira, New York is a snowflake airport, and you have to apply correction when it's minus 22 centigrade or below. That's probably not too often. In Canada, the airlines did their own similar statistical analysis and got Transport Canada's approval for a similar approach. And they have a co-pilot and that app to do a lot of the work. Even Transport Canada teaches their pilots a shortcut. They use a couple of round-numbered percentage corrections to the height difference between each minimum altitude and the height of the altimeter source. That gets rid of the table lookup, but still requires a lot of numbers to be noted down. For the rest of us, every airport in Canada is a snowflake airport, and the applicable temperature is 0 degrees centigrade, or minus 10 for some higher minimums. See the Cap Gen. Wouldn't it be nice if there was an instrument in the panel that gave an accurate indication of the airplane's height without requiring temperature correction and without even needing an altimeter setting. There is such an instrument. Since 2003, we've had one which now works within most of North America. It's called WAAS GPS. In practice, the altitude provided by WAAS GPS is accurate to within about 5 feet over most of the blue area in this map. Note that WAAS is not global, it's North American only. It relies on a set of 28 ground-based stations spread throughout the US, Canada and Mexico, which broadcast correction signals, and geostationary satellites in equatorial orbit, which relay these corrections to users. WAAS navigators display height as GSL. According to the FAA, GSL stands for Geometric Altitude Relative to Mean Sea Level. In fact, GSL is your height above the geoid. The geoid is an irregular, mathematically defined surface that is so close to mean sea level that the difference is negligible. So, for practical purposes, GSL is your height above mean sea level. Earlier, non-WAAS navigators were around 5 times less accurate and were not suitable for vertical navigation. If the integrity of the WAAS component of GPS is not met, it reverts to non-WAAS performance and must not be used for vertical navigation. WAAS GPS altitude is good enough for guidance all the way down the glide path of an RNAV approach with vertical guidance to Cat 1 ILS minimums. So surely it should be good enough to determine all the altitudes on a non-precision approach after you leave your last ATC assigned one. That's exactly what I'll do from this point in the demo. Once I've been cleared for the approach and started my descent, GSL will become my height reference. This doesn't have any official blessing, but it makes good sense to me and apparently meets with the approval of at least one designated flight test examiner. The good news is that the geoid is the datum used by the chart makers, so if your GSL says you're 1,000 feet above an obstruction, you can take that to the bank. And how did the map makers measure the height of that obstruction? With GPS, of course. But they can average readings over a much longer time than we can in the airplane, so they're accurate to a centimeter or so. Many pilots have complained to me that their GPS altitude is usually wrong. On the contrary, their barometric altitude is wrong whenever the atmosphere deviates from the ISO standard model. Where do you get your GPS altitude? That's the only part that's a little less than ideal, since there's no answer which fits everybody's airplane, and the source is probably a bit out of the pilot's line of sight. On the Garmin 400-500 navigators, you can read it at the top right-hand corner of the terrain page. On my airplane, which has a Garmin 530W as GPS number 1, I switch to the terrain page before I level off at the altitude I plan to use crossing the initial approach fix. When I do this, I lose the time and distance to the next waypoint information that I had on the map page, but these are still available on my Aspen primary flight display. That doesn't work on all panels. The Garmin G5 and G500 TXI, for example, don't have quite the same capability, so you won't want to give up the map display. You may have to look for another source. You can always set GPS number 2 to the terrain page, but not everybody has a second GPS. Maybe you have an ADS-B transponder that can display GSL, or a portable GPS that includes a WAAS receiver. On the 600-700 series navigators, you can make it a user-defined data field, so you just stay on the map page. Don't make these corrections to ATC assigned altitudes. They are interested in stopping you from bumping into other airplanes. And as long as everybody uses barometric altitude, they will all be subject to the same error and hence avoid each other. You may bump into the ground, but that's the pilot's responsibility. Here we are in the air, cleared by ATC direct to the Pembroke airport to maintain 6,000. Most of the images of the Garmin GPS, by the way, are taken from the Garmin simulator. It's a lot easier to get a nice steady image that way than using a camera and flying the airplane at the same time. We're maintaining 6,000 on the barometric altimeter. I got the altimeter setting and the temperature at the altimeter source from the Ottawa METAR on XM Weather. It's certainly above 0 degrees centigrade today, so we could fly the barometric altimeter. But on a cold day, we'd have to go through that whole labour-intensive correction process. And on just about any day, attempting to compare the barometric altimeter with numbers from the CDFA table would be an exercise in frustration. So, rather than having a different procedure depending on the season, I now fly GSL summer and winter. ATC has now cleared us out of controlled airspace for an approach to Pembroke. They typically don't specify which approach or which transition to use. At airports in controlled airspace, they'll assign the approach and you may have to specify the transition you want. In a radar environment, expect vectors to final, in which case you won't switch to GSL until you're established on final. Here's the RNAV 35 approach to Pembroke. Remember that we're pretending that the minimum safe altitude is 4,500 MSL, so we'll be able to practice a two-stage descent. Remember also that I picked a top of descent point of 7 miles and 2,800 feet. I'll circle that in the chart. All the other altitudes can be read straight off the chart since we'll be using GSL. I'll load the RNAV 35 procedure into GPS number 1 with the bonded transition. As I do so, note that it shows LNAV plus V in the bottom right-hand corner of the procedure window. That indicates that we'll be getting advisory vertical guidance on this approach. The autopilot will now take us direct to Bondi. If you want to practice with vertical guidance turned off, switch to the appropriate OGS page and disable WAS. Then you'll just see LNAV. I'll load the same approach into GPS 2, then select Direct to Runway 35, so I have a readout of distance to the missed approach waypoint, which is the distance reference for the CDFA table. I can now read this distance at the bottom left-hand corner of my Aspen CDI. I'll use this readout after I've turned final to tell me how far I have to run to my top of descent point. We can now use the VNAV calculator on GPS number 1 to tell us when to start down. We'll specify an altitude of 4,500 GSL, 5 miles before Bondi, allowing us time to get slowed up in level flight before we start the first stage of our approach descent. The VNAV calculator, by the way, works back from your specified bottom of descent to calculate when you should start your descent, assuming that you maintain constant ground speed and match the vertical speed you told the VCalc you would use. I know it says MSL here, but the only altitude the navigator knows is GSL. It will get a slightly erroneous answer if the target altitude is barometric and the temperature at the altimeter source is non-standard. On the 430-530 navigators, we're stuck with that. Just plan to get down a little early so you don't leave yourself tight. Then hit altitude hold on the autopilot when the barometric altimeter or GSL reads the number you're looking for. On the 600-700 series, it's possible to correct your requested bottom of descent for non-standard temperatures, so the target altitude should match the barometric altitude if you take the time to make this correction. In any case, the inaccuracies due to variations in ground speed and vertical speed are likely to swamp those due to temperature. Here, the RNAV calculator says we should start down in about 3 minutes. Here's the message we get when it's time to start down.
From here on, all our altitudes will be GSL, so switch GPS 1 to the terrain page. Here's the message we get when we're 500 feet above our target altitude. That's a little early, but it does give us a heads up to start watching GSL and be ready to push the altitude hold button when it reads exactly 4,500. On my autopilot, I find that gives level flight close enough to the 4,500 for government work.
Although I've lost my time and distance to the next waypoint by switching GPS 1 to the terrain page, I can still read these on the primary flight display in the top left-hand corner of the CDI. I'll slow down to allow me to make a best effort descent after I cross Bondi. Here's our progress on the iPad as we approach Bondi. Crossing Bondi, we start a best effort descent to our top of descent of 2800 GSL. When I reach 2800, I engage altitude hold just before turning final at VIXIB. As soon as the leg inbound to the FAF goes active, the mode changes from terminal to RNAV plus V, showing that we will get advisory vertical guidance. Here we are established on final. I'll switch the autopilot to approach and fly level until we intercept the glide path. On the primary flight display, you see the lateral and vertical deviation indicators appear. I'm 8.9 miles from runway 35 and my top of descent is at 7, so 1.9 miles to go. I complete my approach checks and get the speed down to 100 knots. You can see from the picture-in-picture at the top right corner that my GSL is right on 2800, so the barometric altimeter is reading just a little low. That's not bad considering it's a warm day and we're 70 miles from the altimeter source. With an autopilot like mine, which doesn't have auto trim capability, it's a good idea to briefly disengage altitude hold during this level flight leg to make sure that when you reach the top of descent and disengage altitude hold, there are no unwanted pitch excursions. Also, set the heading bug straight ahead and neutralize the roll trim so that when you re-engage the autopilot on the missed approach, it takes you straight ahead. Approaching my top of descent, my ground speed is around 96 knots. The vertical speed table says we'll need about 500 feet per minute. I'm 7 miles from runway 35 and just about to intercept the glide path. Gear down and a slight power adjustment to stay on the slope. The next check will be CASAM at 1910 GSL. There's CASAM. We're a whopping 10 feet low. OVDUG at 1380 next. Again, pretty close. Now down to the MDA. And here's the MDA. We'll look up and see if we can see the runway. Kill the autopilot and land the airplane. That's about it for 95% of the approaches you'll do these days. RNAV approaches with a CDFA table that's filled in with or without advisory vertical guidance. The next part of this video will look at the other 5%. Until then, blue skies and tailwinds.